Hello students, I welcome all of you in this lecture. In this lecture, we are going to talk about semi-direct products. So first of all, we are going to construct a semi-direct product and via theorem, and then we'll define it. Okay, so let me just write down the statement of the theorem. Theorem, let H and K be groups. Okay, and let phi be a homomorphism from K into set of all automorphisms of H. That means for every element in K, we will define some automorphism of H. So let dot denote the left action of K on H. Let dot denote the left action of K on H determined by phi. Determined by phi. Okay. Further, let G be the set of all ordered pairs H comma K. Let G be the set of all ordered pairs H comma K with H belongs to H and K belongs to K, and define the following multiplication in G. Define the following multiplication in G. Multiplication define कसे केले बघा तर we are taking ordered pairs, right? So H1 K1 ही ordered pair घेतली, दुसरी ordered pair घेतली H2 K2. सो या दोघांमध्ये मल्टिप्लिकेशन असं डिफाईन केलं आहे. तर इट इज इक्वल टू H1 ओके K1 डॉट H2. K1 डॉट H2 म्हणजे डॉट हा जो आहे ती वरची ॲक्शन आहे. डॉट डिनोट द लेफ्ट ॲक्शन ऑफ के ऑन एच, म्हणजे के मधले एलिमेंट्स एच मधल्या एलिमेंट्सवर ॲक्शन घेतात वाया डॉट. ओके, आणि ती ॲक्शन फायनल डिटरमाइन केली जाते. ओके, सो दॅट इज K1 डॉट H2 आणि कॉमा सेकंड जो प्रोडक्ट आहे दॅट इज सिम्पल प्रोडक्ट, म्हणजे सेकंड जे कॉर्डिनेट्स असतील त्यांचा डिरेक्टली प्रोडक्ट करायचा K1 K2. सो या पद्धतीने ही ॲक्शन डिफाईन केलेली आहे. ओके, तर आपल्याला काय काय प्रूव्ह करायचं आहे याच्यामध्ये एकूण आपल्याला 5 पार्ट्स प्रूव्ह करायचे आहेत. ओके, सो लेट मी राईट वन बाय वन. सो पहिला पार्ट जो आपल्याला प्रूव्ह करायचा आहे तो आहे की दिस मल्टिप्लिकेशन, हे जे मल्टिप्लिकेशन तुम्ही डिफाईन केलेलं आहे, दिस मल्टिप्लिकेशन कन्वर्ट्स G into a group. Okay, G into a group of order. It's simple because we are taking order pairs H comma K, that means we are taking Cartesian product. So with order, that's coordinate of G equal to coordinate of H into coordinate of K, right? Okay, secondly we have to prove this part. The sets, there are two sets given. The first set is set of all ordered pairs H comma K where H belongs to H, and second set is given as set of all ordered pairs 1 comma K where 1 is identity element from H. Okay, here we only need to consider K, so K belongs to capital K are subgroups of G, are subgroups of G. Okay, and the maps H maps to H1. Here it should be 1. Okay, just a second, let me just correct that point. Here it is not K, because we are not assuming K, so it is just H comma 1. Okay, so and the maps H maps to H comma 1 and K maps to 1 comma K. These maps are isomorphisms, are isomorphisms of these subgroups isomorphisms of these subgroups H and K respectively. That means H is isomorphic to the first set, that is set of all ordered pairs H1, where H belongs to H, and K is isomorphic to second set, that is set of all ordered pairs 1 comma K, where K belongs to capital K. This is the second part. Third part, we need to prove that H is normal in G. Then fourth part, we need to prove that intersection of these two subgroups H and K is singleton identity. Okay, and the last part that we need to prove, this is the fifth part. Okay, that is for all H belongs to H, okay, and K belongs to capital K, K into H into K inverse, that is equal to K dot H, which is action K dot H, okay, is nothing but phi of K of H. Okay, so these are the 5 things that we need to prove in this particular situation. So let's move to the proof now, and let's try to prove these points one by one. So we're going to move the proof. Let me take the first part. So what we have G equal to, so let G equal to set of all ordered pairs, right? So set of all ordered pairs H comma K, where H is taken from H and K is taken from K, right? Okay, now I want to prove that this set forms a group, okay, and there is proper multiplication defined. So let me just do it one by one. So first of all, I will prove the closure property. So for that, let us take 2 elements from G. So let H1 K1 and H2 K2 belongs to G. Okay, now what happens if you're doing a multiplication? Then what is H1 K1 multiplied by H2 K2, right? But as per the multiplication, it is H1, okay, K1 dot H2, and it's K1 K2. But we can easily find that since this is action, dot जो आहे, but let me write here dot. What is dot? Dot is action of K on H. So comma, so K1 ने जर H2 वर ऍक्शन घेतली या एलिमेंट्सने, तर एलिमेंट रिझल्ट जो येईल तो पुन्हा H मध्ये जाईल, राईट? बिकॉज के टेक्स ॲक्शन ऑन H आणि ॲक्शन म्हणजे ग्रुप ॲक्शन तुम्हाला माहिती आहे की पुन्हा तो एलिमेंट त्या सेटमध्ये जातो, राईट? सो K1ने जर याच्यावर ॲक्शन घेतली तर K1 डॉट H2 हा जो काही रिझल्ट असेल तो पुन्हा H मध्ये जाईल. ओके, सो त्याच्यामुळे H1 मल्टिप्लाइड बाय K1 डॉट H2 हा एलिमेंट H मध्ये गेला, आणि दुसरा जो एलिमेंट ऑर्डर्ड पेअर आहे K1 K2 तो K मध्ये जाईल. सो ऑटोमॅटिकली तुमच्या लक्षात येईल की पहिला कोऑर्डिनेट H मध्ये, दुसरा K मध्ये, म्हणजे याचा अर्थ H1 K1 into H2 K2, that product belongs to G again, right? It's an element of G. So closure property is satisfied, right? Now let's move to the next property, that is associativity. So for that we need to take 3 elements from G. So let H1 K1 comma H2 K2 comma H3 K3 belongs to G. Okay, Now consider for associativity h1 k1 into h2 k2 bracket complete into h3 k3. Let's see what happens with this. So first of all, you have to simplify this bracket, so that is equal to h1 k1 dot h2, right, comma k1 k2 as per the definition of multiplication into h3 k3. So that is equal to h1. Okay, we have to take the first element as it is, right? Okay, so what will we do? We have to take h1 k1 dot h2, right? Then what we have to do, we will see the action k1 takes action on h2, right, in the further part. So this k1 k2 will take action on h2. Okay, so sorry, it's h3. So k1 k2 dot h3 comma k1 k2 k3, k1 k2 into k3, k1 k2 into k3, राईट, हे असं मिळेल. बरोबर आहे. पण याला तुम्ही काय करू शकता, यू कॅन जस्ट सिम्प्लिफाय इट अ लिटिल. सो कसं करता येईल तुम्हाला, कारण ॲक्शन आहे, डॉट इज ॲक्शन. ओके, सो यू कॅन सिम्पली डू दिस. दिस इज h1, राईट, k1 डॉट h2, बट ॲक्शन जे आहे त्याच्या प्रॉपर्टीनुसार दिस इज k1 इंटू k2 डॉट h3, राईट, k1 इंटू k2 डॉट h3. इकडे पण k1 k2 k3 k मध्ये आहेत, k ग्रुप आहे, त्याच्यामुळे असोसिएटिव्हिटी सॅटिस्फाय होते. सो आय कॅन शिफ्ट द ब्रॅकेट, सो आय कॅन राईट इट ॲज k1 k2 k3. So simply now do one thing. Okay, you can take here in the first coordinate h1 as it is, right? Okay, this is k1 dot h2 and this is k1 dot k2 dot h3, right? k1 dot k2 dot h3. So this is simply equal to k1 dot, okay, in bracket h2, okay, into k2 dot h3, simply, right? So that is k1 into k2 k3. Now what is this equal to? So we can simply now look at this h1 into k1 dot something, right, and k1 into something. So this is simply h1 k1 into k1 ने ह्याच्याशी ऑपरेशन घेतलंय, सो kh2 k2 डॉट h3 आणि इथे असेल k2 k3. बट तुम्ही परत सिम्प्लिफिकेशन केलं तर तुमच्या लक्षात येईल की h1 k1 आहे आणि हा जो ब्रॅकेट आहे दॅट इज h2 k2 इंटू h3 k3, राईट. हा ब्रॅकेट कंप्लीट झाला. सो सिम्पली तुमच्या लक्षात येईल की मल्टिप्लिकेशन असोसिएटिव्ह आहे. ओके, सो सिम्पली द ॲक्शनच्या प्रॉपर्टीज यूज केल्या k1 डॉट h2 इंटू दिस एलिमेंट, ओके, k1 k2 डॉट h3, ओके, आणि मग नंतर के ॲक्शन असोसिएटिव्ह मीन्स वी नो दॅट ॲक्शन जर असेल जी, सो जी डॉट किंवा g1 d2 डॉट x इज इक्वल टू g1 डॉट g2 डॉट x. सो ती प्रॉपर्टी इथे यूज केली आहे आणि त्याचा यूज करून पुढचं सिम्प्लिफिकेशन कंप्लीट केलं आहे. सो दिस पर्टिक्युलर प्रॉपर्टी सॅटिस्फाईज द associativity of G. Now let's talk about the identity element of G. So the third part that we are going to talk is about identity. So let me take one element from 1 from G and let me check whether this element is actually an identity. So for that consider any h comma k belongs to G. Now let us see what happens h comma k into 1 comma 1. So that is simple, h as it is, या दोघांचा डॉट, इथे k आणि इथे 1 आहे, सो या दोघांचा डॉट घेतो आपण. सो k डॉट 1 कॉमा, आता ह्या सेकंड कॉर्डिनेटचा प्रोडक्ट म्हणजे k इंटू 1. सो तुमच्या लक्षात येईल दिस इज h k डॉट 1, बट ग्रुपमधल्या कुठल्या एलिमेंटची ॲक्शन जर 1 वर घेतली तुम्ही तर इट विल बी इक्वल टू 1, राईट. सो सिम्पली दॅट इज इक्वल टू k डॉट 1 इक्वल टू 1. ओके, सो इट इज h इंटू 1 होणार आहे आणि k इंटू 1, k इंटू 1 तर kच आहे, राईट. सो लेट मी जस्ट राईट इट क्लिअरली. सो h इंटू k डॉट 1 म्हणजे 1 ओके. सो 1 राहणार तिथे आणि के इंटू 1 म्हणजे के. सो देर इज अगेन एच के. सो इझिली लक्षात येते आपल्याला की हा जो एलिमेंट आहे 1,1 हा आयडेंटिटीची कंडिशन सॅटिस्फाय करतो. म्हणजे ही आयडेंटिटी आहे. वी कॅन गो इन रिव्हर्स पार्ट ऑल्सो. अँड समजा तुम्ही असं घेतलं 1 इंटू एच के, तर 1 ॲज इट इज या दोघांचा डॉट. सो 1 डॉट एच आणि सेकंडचा प्रोडक्ट म्हणजे 1 इंटू के म्हणजे 1 इंटू के. सिम्पल आहे. 1 डॉट एच म्हणजे एच येणार 1ने जर ॲक्शन घेतली तर. सो दॅट इज सिम्पली एच आणि 1 इंटू के म्हणजे के. सो वी कॅन सिम्पली फाइंड thus what is happening here. 1,1 is identity of G. Now let's talk about inverse. Okay, so the last part of the group is that existence of inverse. Now we will calculate the inverse because we are not going to take directly the inverse. We are actually going to calculate the inverse. What is will be the inverse of element? So for that, let us take any element from G. So let h comma k belongs to G, right? And uh, suppose this h comma k into some element x comma y इक्वल टू 1 1 आला समजा, म्हणजे आयडेंटिटी येत असेल तर हा इन्व्हर्स असणार आहे. सो हे सिम्प्लिफाय करत चला आणि एक्स आणि वायची व्हॅल्यू कॅल्क्युलेट करूया. सो याचं काय होणार आहे, मल्टिप्लिकेशन एच पहिला एच आणि इथे जे सेकंड आहे के त्याचा डॉट इथल्या बरोबर. सो दॅट विल बी इक्वल टू के डॉट एक्स आणि के इंटू वाय इक्वल टू 1 1 आलं आहे, राईट. तर तुम्ही जर हे सिम्प्लिफाय केलं, कम्पॅरिझन केलं तर एच के डॉट एक्स इक्वल टू 1 येणार आणि के डॉट वाय इक्वल टू 1 येणार. Okay, sorry, not k dot y, it is just multiplication. So it is not dot, it is not action. So k dot y. Now we have to simplify this. So what happens, this is k dot x is equal to h inverse and इकडे y is equal to k inverse आला, right. But k dot x is equal to h inverse. मग समजा दोन्हीकडे आपण k inverse ने ऍक्शन घेतली, k inverse डॉट घेतला तर कसं होणार आहे, k inverse बरोबर डॉट k डॉट x इज इक्वल टू के इनवर्स डॉट एच इनवर्स येणार आहे, बरोबर आहे. आणि आता ॲक्शन तुम्हाला माहिती आहे की कंडिशन कोणती सॅटिस्फाय करते. सो दिस इज के इनवर्स इंटू के डॉट एक्स इज इक्वल टू के इनवर्स डॉट एच इनवर्स. ओके, पुढचा वाय इक्वल टू के इनवर्स ॲज इट इज ठेवा. सो वॉट दिस इम्प्लाइज, के इनवर्स के म्हणजे 1. सो 1 डॉट एक्स इज इक्वल टू के इनवर्स डॉट एच इनवर्स आणि वाय इक्वल टू काय आहे, के इनवर्स. सो दिस इम्प्लाइज एक्सची व्हॅल्यू आली के इनवर्स डॉट एच इनवर्स आणि वायची व्हॅल्यू आली के इनवर्स. सो व्हॉट इज इनवर्स ऑफ एलिमेंट. सो एच के इनवर्स इज इक्वल टू के इनवर्स डॉट एच इनवर्स कॉमा के इनवर्स. So that will be L inverse of an element, right. So this proves all the properties of group have been verified here. So we can easily conclude that this particular set forms a group. So G forms a group and it's a Cartesian product of H and K, and coordinate of G is equal to coordinate of H into coordinate of K. That's quite simple, right. So this completes the first part that we have proved that G is a group. Okay, fine. After this, let's now move to the second part of this particular theorem, that the sets h comma 1 where h belongs to h and 1 comma k where k belongs to k are these subgroups of G, and we have to establish isomorphism between h and this particular subgroup, right. So let's get started with this particular part now. So what I'm going to do, first of all, I'm going to write down a set which is given to us and I'm going to name it. Okay, so let's try to label the given set like this. So it's the second part now. So let me just label, let us h tilde equal to set of all ordered pairs h comma 1 where h belongs to h, right. So our claim is that we have to show that it is a subgroup of G, right. But in that case we have to consider two elements of this and we have to prove that, means this particular criteria means if you want to prove that something is a subgroup, then take two elements from that particular set and prove that xy inverse is also in that set. So let me take two elements from here now. So let h1 comma 1 h2 comma 1 belongs to h tilde, then h1 comma 1 into h2 comma 1 inverse equal to, so this is equal to h1 comma 1. What is h2 1 inverse? So if you can easily go to back and you can find out hk inverse काय होतो, तर k inverse dot h inverse आणि in comma k inverse हा hk चा inverse आहे. So h2 1 चा inverse काय होणार आहे, 1 inverse dot 1 inverse dot h2 inverse, ओके, आणि सेकंड कोऑर्डिनेटमध्ये 1 इनवर्स, म्हणजे h कॉमा k असेल तर k इनवर्स डॉट h इनवर्स म्हणजे 1 इनवर्स डॉट h2 इनवर्स कॉमा k चा इनवर्स म्हणजे 1 चा इनवर्स, राईट. सो हा झाला इनवर्स h2 कॉमा 1 चा इन g. सो दॅट इज h1 कॉमा 1 1 इनवर्स म्हणजे 1 येणार डॉट h2 इनवर्स येणार इथे 1 चा इनवर्स 1. सो दिस इज इक्वल टू h1 कॉमा 1 1 dot h2 inverse म्हणजे it is h2 inverse as per the definition of action comma 1. So this is equal to h1 into h2 inverse comma 1, but h1 h2 दोन्ही h मधलेच आहेत, राईट, त्याच्यामुळे h1 h2 inverse पण h मध्ये असणार आहे. So this particular element belongs to h tilde, right? So that's why clearly we can, let me write reason, since h1 and h2 both belongs to h, so that's why this h1 h2 inverse belongs to h, and this clearly means that h tilde is a subgroup, right? Now let me establish the isomorphism between h tilde and h. So define a map between h tilde and h to establish that isomorphism. So define a map. Let me name that map as suppose alpha. So alpha is a map, or rather we may take another symbol. So let me just take f, map from h tilde to h, as how to define it, f of h comma 1 will be equal to h. So this is what we're going to consider map. आता बघूया की हा मॅप वेल डिफाईन्ड 1 1 ऑन टू आणि होमॉर्फिझम आहे का. सो पहिला पार्ट यातला एफ इज वेल डिफाईन्ड. सो एफ इज वेल डिफाईन्ड दाखवण्यासाठी वी हॅव टू कन्सिडर टू एलिमेंट्स आर इक्वल. सो लेट h1 comma 1 h2 comma 1 belongs to h tilde such that h1 comma 1 is equal to h2 comma 1. So this implies if we'll consider the ordered pairs, then we can easily find out that h1 is equal to h2. But as per the definition, h1 means this is f of h comma 1, sorry, f of h1 comma 1 equal to h2 means as per the definition f of h2 comma 1, right? So let me just check, can I go in reverse direction? f of h1 comma 1 equal to f of h2 comma 1 घेतलं म्हणजे इमेजेस इक्वल घेतल्या दोन एलिमेंटच्या, तर अकॉर्डिंग टू डेफिनेशन h1 equal to h2 and h1 comma 1 equal to h2 comma 1. So yes, we can go back, so we can trace it back and I can show that it is 1 1 also. So f is well defined and 1 1. Now let's prove that f is onto. It's quite simple. So second part, f is onto. So for that consider any h belongs to h. You can clearly find out its image, sorry, pre-image. Then clearly h comma 1 belongs to h tilde such that f of h comma 1 equal to h, right? F of h comma 1 equal to h ala. And what this means f is onto, right? So this implies f is onto because you found its pre-image in h tilde. And last part, that I want to establish an homomorphism. So I want to prove that f is homomorphism. So for that I had to take two elements from domain. So let h1 comma 1 h2 comma 1 belongs to h tilde. Let me just tell you in the short how can we prove that homomorphism. So we have to prove this particular part, f of xy is equal to f of x into f of y in general for any elements x and y in domain. So here f of h1 comma 1 into h2 comma 1, right? we have to prove that this is equal to f of h1 comma 1 into f of h2 comma 1. But let's try to find out f of what is multiplication, how we define the multiplication. So it is h1, right? Then we have to take action of this element on this element. Okay, so the second element will be equal to h1 1 dot h2 comma, then we have to take the product of second coordinates, so 1 into 1 1, right? So this is equal to f of h1 1 dot h2 means h2 as per the definition of action comma 1, but this is equal to h1 h2 according to definition of f. So this is, but h1 is what? H1 is f of h1 comma 1, and what is h2? H2 is f of h2 comma 1. So we established isomorphism. So f is well defined 1 1 onto an homomorphism. So hence f is isomorphism. F is isomorphism, and which sets are isomorphic, and h tilde is isomorphic to h, domain is isomorphic to codomain. That means what is h tilde? Set of all elements of this type h comma 1, where h belongs to h is isomorphic to h, right? Now similar process we can follow for k, right? Instead of h, if you are talking about k, then you have to follow a similar process. Just you have to define a map in a different manner so that you can establish the isomorphism between 1 dot k, where k belongs to k, and k itself. So let me just give you the hints so that you can establish that isomorphism. So what is my next part? Let k tilde equal to 1 comma k, where k belongs to capital K, right? Okay, we have to prove that it is a subgroup. So again we have to use the same methodology. We will consider two elements from k tilde. So consider 1 comma k1 and 1 comma k2 belongs to k tilde, and prove that 1 comma k1 into 1 comma k2 inverse belongs to k tilde. So that will be a subgroup. Then it's a very simple, so it will be left an exercise. So then k tilde is a subgroup of G, right? And to establish isomorphism between this set and k, define a map. It's very simple. Define a map, say G from k tilde to k such that G of 1 comma k equal to k. As a map define kara, and prove that it is isomorphism using the same methodology that we have adopted in the previous discussion. So prove that G is isomorphism. Okay, so this will be an exercise. You can handle it easily, right? So this proves the second part of the theorem, that h tilde and k tilde are subgroups of G, and h tilde is isomorphic to h and k tilde is isomorphic to k. Now let's go to the third part and let's establish that h is normal subgroup of G. Okay, but before proving that, what we will do, we will prove the fourth part and fifth part, and using those conditions we will establish the third part. So let me go to the fourth part now. So what we have to prove, our claim is that h intersection k is equal to singleton identity. So there is only identity element in common, right? But what we have just established something. We have proved that h tilde is isomorphic to h and k tilde is isomorphic to k. So any element of h can be identified as element of h tilde, and any element of k can be identified as element of k tilde. So let me take two elements. So let x belongs to h intersection k, right? So this implies x belongs to h and x belongs to k. But if x belongs to h, then h is isomorphic to h tilde. So we can take x comma 1 belongs to h tilde, right? Because x belongs to h, so these are isomorphic. So x comma 1 belongs to h tilde, and x belongs to k also, so 1 comma x belongs to k tilde. Okay, so what happens if we'll consider this? Okay, then what is intersection between these two, but let me establish that part. If we take two elements, okay, so if we take one element common in h tilde and k tilde, so suppose the, but if a comma b belongs to h tilde intersection k tilde, okay, then what happens? Then a comma b can be written as a comma 1, okay, because it is in h tilde, and a comma b can also be written as 1 comma b because it is in k tilde. So if we will compare this, you will find that a equal to 1 and b equal to 1. So this what means? This means h tilde intersection k tilde इक्वल टू सिंगलटन 1 1 हा एकच एलिमेंट त्यांच्या दोघांच्या इंटरसेक्शनमध्ये आहे. सो इथे एक्स कॉमा 1 बिलॉंग्स टू एच टिल्डा, 1 कॉमा एक्स बिलॉंग्स टू के टिल्डा. सो ॲट अ टाइम हा एलिमेंट जो आहे एक्स, तो एक्स कॉमा 1 पण लिहू शकता तुम्ही, 1 कॉमा एक्स, कारण दोन्हीमध्ये आहे तो. सो ह्या दोघांमध्ये पण आहे. सो आयडेंटिफाय केला तर यू विल फाइंड दॅट एक्स इक्वल टू 1. ओके, सो आयडेंटिटी, let me just rename that equation. Suppose this is star. So from star, x equal to identity, right? Why it is identity? कारण x h मध्ये होता, राईट, आणि x k मध्ये पण होता. बट x h मध्ये आहे म्हणजे त्याला आपण असं लिहू शकतो, बट तो k मध्ये आहे म्हणजे याचा अर्थ तो इथे गेला तर x ची व्हॅल्यू 1 झाली. तसंच इकडचा एलिमेंट x k मध्ये आहे म्हणजे तुम्ही त्याला हा असा आयडेंटिफाय केला, राईट, हा तुमचा आयडेंटिफिकेशन. बट सेम एलिमेंट h मध्ये पण आहे म्हणजे h टिल्डा मध्ये आहे म्हणजे हा एलिमेंट इकडे गेला म्हणजे सेकंड कोऑर्डिनेट 1 असायला पाहिजे. सो x ची व्हॅल्यू 1 येते. सो इन शॉर्ट x इज इक्वल टू आयडेंटिटी. Now we will prove the fifth part. Okay. Okay. Now let's move to the next part of this theorem. So as I told you, we will prove the fifth part first of all. So what I want to prove, let's just jump to the fifth part of the theorem and let's see what is given there. So we have to prove that for all h belongs to h and k belongs to k, kh k inverse is equal to k dot h. That is phi of k applied on h. So that is what the action. Okay. So action of k on h, we have to establish that action. So let's have that. So for this, what I will do, I will take one element from h. So let h belongs to h, and I will take one element from k, that is small k belongs to k. But what I know that h is isomorphic to h tilde, right, and k is isomorphic to k tilde. So definitely I can write this. I can write this h as h comma 1, and okay, and I can write this k as 1 comma k. So try to now, what is k h k inverse? So you can replace k by 1 comma k, you can replace h by h comma 1, and you can replace k inverse by 1 comma k inverse. But let me just remind you that how do we take the inverse of h comma k? So inverse of h comma k is nothing but k dot k inverse dot h inverse comma k inverse. That is what the inverse of h1 comma h comma k. So if I will substitute that value here, then it will be equal to 1 comma k, then it's h comma 1 and 1 comma k inverse. So this is simply k inverse dot h inverse. So k inverse dot h inverse means 1 inverse comma k inverse, right? So you have to just do the multiplication here. So what will happen now? So here, what is 1 comma k into h comma 1? So 1 comma k into h comma 1 is simply 1, then k dot h, right, comma k into 1, that is k, okay, into k inverse dot 1 inverse, but k inverse is k, k inverse is k inverse, 1 inverse is 1, so comma k inverse. Let's simplify it further. So this is simply equal to 1 into k dot h, so that is k dot h comma k, then it's k inverse dot 1, so that is equal to 1 comma k inverse. So simply this is k dot h, okay, then it is simply k dot 1 comma k into k inverse. So as I'm telling you, first element as it is, right, then act this element on this element, so k dot 1, and product of second elements, so k into k inverse. So what is that equal to now? So that is k dot h, right? K into 1 is 1, so k into k is 1, so k dot h comma 1. So you can identify this as element of h because second coordinate is 1. Okay, so simply what can I say? This implies kh k inverse is equal to k dot h, right? So that is what we wanted to prove, and k dot h means phi of k of h. That is how, because phi is homomorphism. Okay, phi is automorphism of h, I think. Let's have a quick look at that. So yeah, phi is homomorphism from k into automorphisms of h. So if you're taking one element from k, then phi of that k means phi of that k will be automorphism on h, so it will apply on h. So this is kh k inverse, that is k dot h, and that is phi of k of h. Now let's move to the last part, which is third part of this theorem. I want to prove that my claim will be h is normal in G. That is what I want to prove. So it's very simple. Let me just remind you the logic. How do we prove that something is normal? So if I want to prove that H is normal in G, then I have to take one element from H. Then I have to take one element from G. Okay, and I have to prove that conjugate GH G inverse belongs to H again. Right? That is what my target is. So do. So let one element take one element H belongs to H, and okay, and take one element G from G. So suppose I'm taking H dash K dash from G, right? But since I can identify each element of H as a H comma 1, so this is simply H comma 1, but I have one more trick here, so which I can use. Okay, so since we have proved something, K is K inverse is equal to K dot H, that is phi of K of H, so that is subset of H, right? So let me just use that point. Instead of having this regular definition, we can use the previous part to prove this. So let us go by that method. So what we know that kh k inverse, okay, is equal to k dot h, right? And that belongs to h. Okay, so simply what can I say? So every normalizer of h means you are taking h, तुम्ही h घेतला, h मधला एक एलिमेंट आणि त्याला नॉर्मलाइज केलं, तर नॉर्मलाइज केल्यानंतर सुद्धा तो परत h मध्येच जातोय, राईट? सो होतंय काय की k हा h मधल्या प्रत्येक एलिमेंटला नॉर्मलाइज करतोय. म्हणजे बेसिकली व्हॉट आय वॉन्ट टू टेल यू इज दिस, व्हॉट इज नॉर्मलायझर ऑफ एच? सो नॉर्मलायझर ऑफ एच म्हणजे असे सगळे एलिमेंट्स की जे एचला नॉर्मलाइज करतील. सो इन शॉर्ट वी कॅन टेक जी बिलॉंग्स टू जी सच दॅट जी एच जी इनवर्स इक्वल टू एच, किंवा जी एच जी इनवर्स बिलॉंग्स टू एच फॉर ऑल एच बिलॉंग्स टू एच. दिस इज वॉट द डेफिनेशन ऑफ नॉर्मलायझर, म्हणजे जो एलिमेंट एचला नॉर्मलाइज करेल, राईट? इथे जर तुम्ही पाहिलं तर के मधला तुम्ही एलिमेंट घेतला होता, हा तुमचा के मधला एलिमेंट आहे, हा एच मधला एलिमेंट आहे, रँडम एलिमेंट, आणि तुम्ही पाहिलं की के एच के इनवर्स जो आहे तो पुन्हा एच मध्ये जातो. म्हणजे हा जो के आहे तो या एचला नॉर्मलाइज करतोय, बिकॉज के एच के इनवर्स बिलॉंग्स टू एच फॉर एव्हरी एच. ओके, so that means k normalizes that subgroup H. So I can use that idea and I can write here that k is contained in normalizer of H. Okay, so what this implies? This implies k is subset of normalizer of H, right? But already every subgroup normalizes itself, so H is also subset of normalizer of H, right? Okay, so what will happen? H k is subset of normalizer of H, H is subset of normalizer, so this implies H into K is contained in normalizer of H, right? Okay, but what is H into K? Because it is given that H into K equal to G. Okay, because H into K is isomorphic, H is normal, H into K is isomorphic to H cross K, because we have proved that H intersection K is singleton identity. So what can we use? So HK, that is G, so G is contained in normalizer of H, so that means normalizer of H is equal to G, because, and that means because G is subset of normalizer of H, but G is the group, so it must be equal to normalizer of H. So that means normalizer of H equal to G, and that means H is normal in G, right? Okay, so hence H is normal in G. So that was the final part of the theorem. Okay, so let me clear this point, because you must be finding this surprising that how hk is equal to g. So let me just elaborate that point. So suppose I'm taking one element from h, so I can write it as h comma 1. If I'm taking one element from k, I can write it as 1 comma k. Do the multiplication of these elements, because this multiplication belongs to hk, right? Do this multiplication, you will find that h as it is, 1 act on 1, 1 dot 1, and 1 into k, that is k. So h 1 dot 1 is 1, so h into 1 is h, so that is h comma k, and this belongs to g, right? So simply you can find that h into k is subset h into k. Every element is a element of group. Okay, so that's why g is equal to hk. Okay, so this is equal to g, belongs to g. So in fact h into k equal to g, that is what the point is. So we have proved that this particular group satisfies all these conditions, because we have to define map in that manner. Okay, so in the upcoming lecture we will discuss about semi-direct product, and semi-direct product is nothing but the product of subgroups h and k that were defined here. So आपण h घेतला होता, k घेतला होता, त्या पद्धतीने आपण phi डिफाइन केला, होमॉर्फिझम फ्रॉम k इंटू ऑटोमॉर्फिझम ऑफ h, आणि ॲक्शन डिफाइन करून आपण जो जी आहे ऑर्डर पेयर्स एच कॉमा के, त्याला ग्रुपमध्ये कन्वर्ट केलं होतं. तर हा जो ग्रुप आहे तो एच आणि के पासून कन्स्ट्रक्ट केला आपण या मॅनरने. सो याला आपण म्हणतो सेमी डायरेक्ट प्रोडक्ट. वाय डोंट यू कॉल इट डायरेक्ट प्रोडक्ट, वी जस्ट कॉल इट एज सेमी डायरेक्ट प्रोडक्ट. ओके, बिकॉज याच्यामध्ये फक्त एकच सबग्रुप नॉर्मल असतो. ओके, ओनली एच इज नॉर्मल. ओके, so with this I stop here. Thank you.